All right, so let's work this problem. It says find all the forces in the truss. What else do we know? It's got a load P on the end, so we'll be finding everything in terms of P. Now, we talked about zero force member just a few seconds ago. Do you see any potential zero force member scenarios? Let's talk about that case one. Case one was two members at a joint, no load at the joint. Do you see any of those? Well, here's two members at a joint B, but there is a load. There's two members over here connected at a joint, but the reactions also count as forces. So I don't see any. Is there a case two possibility? Three elements, two collinear. There's three there, but two are not collinear. There's three there. Again, two are not collinear. So that's it. We're at a. So there are no zero force members by inspection in this truss.
It has to be three, right? It can't be like it's like an E. You have.
No, right now I can't say that any of those are zero by inspection. Now it's possible that they will be zero under certain loading cases, but not by inspection. So we should proceed. So the first step we always do is get as many of the reactions as we can. I guess I should also ask, is this structure externally stable? So I've got a pin at A and a rocker at F. Are my reactions all parallel? No. Are they all concurrent? No. So I think we're externally stable. What about internally? Just looking at the truss. I see nothing but triangles. I think we're all solid there. So this is a stable and determinate system. So let's begin. I will assume, I'm going to use this as my free body diagram. So I'm going to assume I have an unknown AY, a horizontal AX, and then here at E, I'll assume it also acts up. I'll call it EY. So there's my three external reactions. So let's solve those. What's the best thing to do here? I guess I could sum forces in the X direction, find AX pretty quickly. If I sum forces in the Y direction first, I have two unknowns, one equation, so that's not a good start. So I should probably sum moments somewhere. A is a good place. You could also do it at E, but I like to do it at a pin, so we'll sum moments at A first. So I'm going to use right-hand rule for my sign convention for my moment. So we're going to sum moments about point A and set it equal to 0. So looking at point A, let's look at the applied load P. What kind of moment does it create about A? Positive or negative? Negative. So I'll have negative moment, and it's created by the force P. And what's the distance between A and P?
8.
Looks like 8 meters. The other force creating moment about A is EY. What kind of moment is that? Positive or negative? Positive. So I have a positive moment, and I have a force, EY, times a moment arm of 4. Well, that's pretty easy to do. So EY is going to be what? 2P. Yes?
I didn't realize that we would be using P as like kind of like a constant.
It's just some force P. It can be anything.
Okay. I didn't realize. I thought there was like 4 unknowns, so it's like you only have 3 equations.
No, we know the load. We don't have a numerical value, so we're solving it symbolically. So we're actually going to find all the forces in terms of P, and it could be for any load applied there. P could be 0 to whatever number you chose, and you would just plug that value in for P, and you'd have the value, the loads. Not to give too much away, but we're going to be doing something very similar to this when we start doing our analysis for our project. But I'll save that for later. All right, so what do we do next? It doesn't really matter, but I'll just go ahead and sum forces in the Y first. So again, I'll assume up is positive. So we'll sum forces in the Y direction. Make sure it's in equilibrium. So I've got AY acting up, EY is acting up, so those are both positive. And anything else? Nope. Nope, I missed one. Minus P. Sorry. P is down. So I should be able to solve for AY. And AY looks like it's going to be negative P. And that kind of makes sense too. If you kind of think of this as like a seesaw, I'll put my point there. If I pull down P on this side to keep this thing in balance, I need to pull down P on this side. So I assumed up, that's why I got the negative sign, and the magnitude balances. They have the same moment on. It's like a balance. And then just to be complete, I'll sum forces in the x direction. And in this problem, I only have AX to the right, so that's positive. And you can see it's the only term, so it's 0. So I got 3 unknowns. My next challenge is to get all the bar forces. There's 1, 2, 3, 4, 5, 6, 7 more things to do. We've got some work to do. So looking at a strategy of how to proceed, where would be a good place to do method of sections? Method of joints. Well, right now we can only write 2 equations of the joint, so I only have to generate 2 unknowns. So D would be a great place because I've got 1, 2 unknowns. How about A? A would work because I've already found AX and AY, so there's 2 there. So A and D would work. Could I start at B? No. How about same argument for C? There's 3 unknowns, only 2 equations. Of course, E would be the worst place to start because you can only write 2 equations in 4 unknowns. You probably want to go to E last. So I'm going to start at A simply because A comes before D. So I'm going to start at joint A, and I'm going to draw all the forces acting at that joint. So there's joint A. I found AY to be minus P, so that means it's down. And AX is 0, so there's my applied forces at A. And then I'm going to assume that I have a tension force from A to E and a tension force AB. And in this particular case, the angle is 60 degrees. So there's my free body diagram for the joint at A. And again, remember, I always like to assume tension. I'm going to suggest you do the same. And remember, the advantage of that is if I get positive values in my equations of equilibrium, tension's tension, positive's positive. If I get negative, I know they're compression. And that's this kind of sign convention that we use in structural engineering.
Why didn't you use AX like on there?
AX is 0.
Okay.
There's no point in putting it there, right? It's 0. And I also went ahead and made AY minus P, so it's down. So when I got a negative for Y, I didn't run back over here and change this. But as I draw a new free body, right, can now make any kind of assumption I want, I went ahead and made the correction to keep it easier for me. So we can write 2 equations, some forces X, some forces Y. Which would be the easiest one to do first?
1.
Yeah. AE and AB both have X components, so that'd be one equation, 2 unknowns. That's not a good place to start. So we'll sum forces in the Y direction first. So again, I'll assume up is positive. We'll sum forces in the Y. Make sure it's in equilibrium. The Y component of FAB will be the what? Sine or cosine of the angle? Sine. So I'm going to have FAB sine 60. That's the pot that's going up, and then I'll have P going down. So what is the force in AB? It looks like it's positive.
2 radical 3 over 3 P.
Yeah, what is sine of 60? That's
Radical
square root of 3 over 2.
Square root of 3 over 2 and then flip it over. Oh, you already flipped it over? Pretty sweet, huh? Easy. You guys are really quiet. Is this okay?
It's 2 radical 3 over 3. Because you got
What is it?
radical 3 over 2 is sine 60. You got to flip it, right?
I don't know. I asked you. You told me. This is what I wrote down. What you told me.
No, I told you 2 radical 3 over 3.
2 radical 3 over 3. Is that right? Do this for me. Compute the sine of 60
Yeah.
and invert it. What is that number?
Yeah. 2 square root of 3 divided by 3.
Just give me the number.
1.15.
Point. What is it?
1.15.
1.15? I'm really messing this up. 1.15 p. I think I should get my own calculator. Is that right?
Would you accept P divided by sine 60?
You can do that, sure.
Okay.
I don't care.
I was confused.
So now what do you do? Some forces in the x direction. So I've got the force F AE is to the right, and then I have the x component of AB, which is the cosine of the angle. And they're both positive. But I know AB, so I can put that right in there. So I should be able to solve for FAE. And that looks like it's going to be negative. What is that?
0.58
That sounds reasonable.
P.
0.58?
77.
0.58. Okay. It's 877? No, that's good. That's good enough.
It's 577, but I was just...
What? Okay, so 0.58 is rounded already?
Yes.
Okay. All right. So we'll just stop for a second and see what we've got. So I found that AB was in tension and AE was in compression. Does that make sense? Let's see. When I pull down on this thing, is point D going to go up or down? Down. So it's going to probably stretch this one in compression. So it looks like this whole top chord is going to go in compression. So that makes sense. Is point D going to go to the right or to the left, do you think? Probably going to move a little to the left. So this, I said that wrong. This is tension, this is stretching. So tension, this is all going to kind of compress a little bit. Because when you pull it down, F won't try to get longer. It'll probably go this way. I'm just. That's my rationale. You may not see it. It's not crazy important. I think the only one that should be more obvious. It's kind of obvious. Is more obvious is the top going into tension. These inside are going to be a little harder to see. I think they're going to be all in compression. But let's see what happens. So we got 2. So now where do we go? Can we go to B? We could, because we have AB. We still can't go to C. We still can't go to E, but we could do D. So I'm going to come back and do D. See, these problems are kind of tedious. So starting at D, I've got my applied load acting down, P. I'm going to assume tension in force DE and tension in force CD, and it's the same interior angle. In fact, if you look at these two guys, they're pretty much the same, they're just kind of mirrored. So as we go through this equation again, we ought to find out that we get the same results for kind of the matching values. Hopefully that will work out. So using the same strategy we did for joint A, it's probably a good idea to start summing the forces in the y direction. CD is the only unknown with a y component. So we'll have the force in CD, sine of 60, that's the vertical component, that's acting up, and then minus P is acting down. So when you solve for the force in CD, hopefully you get 1.15. Is that right, Mr. Bellis? We get that again? Sure? That didn't sound very confident. Sure, why not? Whatever. Okay? And then we sum forces in the x direction. So now we have the force DE to the left, so that's negative, and then the horizontal component of CD, which will be the cosine of the angle. Again, if we plug that in there, we should find that the force in DE is negative, and hopefully it's that value. Is it? 0.5777777, but we'll just say 0.58 P. So again, we found this to be in tension, this to be in compression. Now at this point, we can proceed any way we like. There's no bad choice, I guess. You could go to D. Again, there's only two unknowns. You could go to C, two unknowns. You could even go to E. There would be only two unknowns. But I'm still not really excited about E yet. So just for alphabetical reasons, I'm going to start at B. I kind of run out of space, so I'm going to pop a new one on top and let us work on B and C. So let's go to joint B. So I'll draw a line here. So what do we have? We've got a force from AB. We've got a force from BE. And then we've got a horizontal force between BC. I'll just put a little geometry here. I know this angle is 60 and this angle is 60. Also from our previous work, we already know the force in AB. That's something we know. So we can bring that along. So now looking at the two things that we don't know, BC and BE, looking at our two equations, summing forces X or Y, which would be the easiest one to do first? X or Y? Y. This is the only one with a Y component, right? So I write one equation in, one unknown. If I try to sum forces in the X direction here, I get one equation in, two unknowns. Don't want to do that yet. So let's sum forces in the Y first. And see what we get. Well, both these Y components of AB and BC are down, so that makes them negative. So I'll start with the first one. It'll be FAB, and that will be the sine of 60 degrees, minus the force in BE, also sine 60 degrees. So they have a common sine 60, which I can just factor out. And that just says that the force in BE is equal to minus the force in AB. And what's the force in AB? I believe, I have to look back, 1.15. So was it positive or negative at AB? It's positive, so this will be negative 1.15 P. So BE is in compression. So now I can finally sum forces in the x direction. Everybody's got a component in the x direction. So I'll just work my way this way. So starting with AB, it's going to the left, so that's negative. So I'll have the force in AB times the cosine of 60. As I swing around here, BE and BC are to the right, so that's positive. So I'll have plus the force in BE cosine 60. And it counts for these two. And then plus the force BC. So I have those two values. I can plug those in here and here, and I should be able to solve for BC. What is that? Well, this is negative, so it's going to be a positive number. What's the cosine of 60? Is that 0.5? So it's going to be 1.15 again? So BC is in tension, and BE is in compression. Now remember from before, we found this was tension, this was compression. This was tension, this was compression. Just update those. So we only really have one unknown left. CE. I still don't want to go to joint E. That's a lot to take care of. So I guess my only choice is to go to C. Now in this problem, fortunately for us, C and B are kind of mirror images of each other. So if I look at what I have, at C, I have the force in CD, which I've already solved for. I have the unknown force, the last one I'm looking for, which will be CE. And I have the horizontal force, which is the force BC. Just to help you keep track, I know that one, and I know that one. I'm just trying to find this guy. Can I do that with just one equation? I need to put my geometry in. Just give me a second. So how can I find C? Oh, I'm almost out of room down here. How can I find CE? What's the easiest equation to use? Probably the one that requires the least amount of information. So they all have X components, but only these two have Y components. So I think probably the Y component would be the easier one to do. So if I come back and sum forces in the Y direction, what do I have? Well, I've got my unknown down here. and they're both going down, so that'll be minus the force in CE, and that'll be the sine of 60, minus the force in CD, also sine 60. Well, the signs again cancel, and you can see that the force that we're looking for, CE, is just minus the force from CD. And where's CD? I have to go back a page here. CD was 1.15. So this becomes minus 1.15. And it's compression. So we're all said and done. It looks like the whole upper cord is in tension, and all these elements that kind of spoke out from the center here, kind of like spokes on a bicycle wheel, are all in compression.
I have a question. Is A and C is similar, like, is it similar?
What's that?
C and B?
Yeah, they are. See?
Yeah.
B and C are the same, it's just they're kind of mirror images. And if you look at the equations that we got when we sum forces in the y direction, it's very similar. Okay, wasn't that exciting? That only took 27 minutes. Huh. You get 15 minutes on the exam.
On the exam, problems?